So welcome back, Level 2 physicists, continuing on with our internal around nuclear and atomic energy, or physics. Today looking at fission and fusion. So remember from our last lesson, we calculated the binding energy of the iron 56, okay, the energy required to bind all the nucleons to form an atom of iron 56, and we found out that the binding energy using Einstein's equation was 7.83 times 10 to the negative 11 joules. Okay, so what does this actually mean? Well, essentially, it's the energy that is being used to bind all those nucleons into the nucleus. Okay, and that's the reason why we have that mass defect, that the mass that is lost is being used to create that binding energy to form the nucleus of the atom of iron 56. So in terms of nuclear fission, what happens in nuclear fission is that a slow moving neutron basically hits an isotope of uranium, uranium-235, that creates an unstable isotope of uranium called uranium-236, and that breaks down or causes a fission, a breaking up of the uranium-236 isotope into two daughter nucleotides, barium-144 and krypton-89. And because we've also got the binding energy, which is in the uranium-236 nucleus, that's also released. So you've got the release of binding energy, the release of gamma radiation, and also the release of 3 more neutrons, okay, in the formation of those daughter nuclides. And this causes a chain reaction, because if you've got uranium-235 atoms adjacent, then those 3 slow-moving neutrons are therefore going to hit more uranium-235, and that basically causes a chain reaction which creates nuclear bombs, okay, because lots of energy obviously is released, and every time a uranium-235 is broken up into its daughter nuclides, that releases further neutrons, so it continues going on and on until all the uranium-235 is used up. The other type of nuclear reaction we'll look at also is nuclear fusion. So essentially what happens is in nuclear fusion, it's an isotope of hydrogen known as deuterium fuses, okay, joins together with another isotope of hydrogen called tritium, okay, and that fuses together to form helium, and there's also 1 neutron released, and binding energy is also released as well. Okay, so that's known as nuclear fusion, because you're fusing, you're bringing the deuterium and tritium isotopes together to form the helium. So in terms of the conditions of fusion, they're commonly found in stars, because it's a lot harder to do fusion reactions on Earth than it is to do fission reactions. So for fusion, what you need is high temperature and high pressure, and that's why stars are a perfect place for that to occur, and that's what actually powers our sun, for example. It's actually nuclear fusion. Okay, we've tried it on Earth to try it as a fusion as a power source, and because essentially what happens is that due to the high temperatures, a plasma is formed, which is charged. Strong magnetic fields are used to control the nuclear fusion reaction, okay, in something called a torus, which you see there. But the problem is that the energy required to run the magnetic field is actually more than the energy released in the fusion reaction. So we're still a work in progress, at least on Earth, to do nuclear fusion. So in terms of fusion versus fission, basically isotopes which are on the right side of iron 56 undergo fission to stabilize, whereas isotopes to the left of iron 56 in terms of stability undergo fusion to stabilize. So that's your heliums and your hydrogens and your tritiums, your isotopes of hydrogen and isotopes of lithium. And those are actually the isotopes that are found in stars, because that's where basically where nuclear fusion occurs in the universe.